Okay. Good morning, everyone. Welcome to another section. I remain Favor and I am your host for this section. And for today's topic, we'll be looking at the network lab experience, your hands-on guide, where you will learn networks, the type of networks and components, and you also be introduced to network security before we move on to the hands-on section. So before I hand over to our facilitator for today, in case you are joining us for the first time, you have to create your account on hack365global.com. And to be able to access that, you need to first create an account on sitechacademy.com and then use those login details on hack365global.com. And you have access to labs. Finally, for questions, if you have any questions, please note them down and they'll be attended to at the end of this section. And for the online participants, please just drop your questions in the comment section and they'll be attended to. I guess that's all. I'll be handing over now to our facilitator. We have a new facilitator for today. His name is Cedric. I wish you a happy learning experience. So see you at the end of the section. Cedric, you can take over.
Is better now. Okay. Excellent. Claire, there right now. All right. So Good day, everyone. Welcome, and thank you all for joining in. My name is Abakar Ogirma, Abakar Sadiq Ogirma. Just as Dave has said, we would be going through network security. And to be able to do that successfully, we need to understand some of the core fundamentals. And we're going to start with networking. So as you can see on the table of contents, we'll get into understanding networks first. We'll break down network types and components. Then we would now have a proper introduction into network security. And lastly, we would have the hands-on lab, which would be on Cisco Packet Tracer. So without wasting much of our time, let's get started. So a computer network, right, at its core, is the collection of interconnected devices that can communicate with each other. And this allows for sharing, and also based off of that, the internet itself is made possible. So the internet is comprised of a lot of devices, and all of these devices can be referred to as nodes. And these nodes participate on the network at different capacities, right? But by virtue of definition, a node could be a computer, it could be a printer, it could be any other device, as long as it is either sending or receiving information on a network. So for resource sharing, you usually need to have computers, servers, and routers, right? These are for a basic network. But it's important to know that a network could be simple, a network could be complex. So first, to speak about some of the important fundamentals and things that you need to know about network infrastructures and network components. What you can see on your screen now is a MAC address. The MAC address, it's a unique identifier assigned to a network interface card, which is usually referred to as a NIC. And it is burnt into the NIC card and it isn't really changed. This is done from the manufacturer side, right? And then it's used for communication on the layer 2, which we'll still speak about when we get to another section of this training today. So it is done on layer 2, which is the data link layer of the network segment. And it is usually represented by unique serial numbers that is, like I said, on your network card, right? But like you usually don't have access to the network card. It's not something you can see physically, but it's something that you can prove from your system. And then you can find that information out. So to get into networks and understanding how networks, work from a basic perspective to a wider perspective, right? On your screen, you can see that I've broken down these networks into three: the LAN, the WAN, and the MAN. We're going to be discussing about these three to understand how each of them play into each other and what you see generally today as a network. So a LAN is usually a small, high-speed type of network, right? If you have two PCs connected to each other, like in the past, PCs were usually connected via a cable, an RJ45 cable, or the type of network cable, but most popularly an RJ45 cable, and they are able to communicate with each other, right? But as the internet has grown, now you have Wi-Fi network becoming the more popular type of, that's the wireless network, becoming the more popular type of network that is being used around the world and everywhere as we go. So by definition, LAN is a small high-speed network. You have few numbers of PCs interconnected with other networking device sometimes to create a network. So as the distance increases, as we know, like for instance, there's here and all of the PCs together, there are like maybe 3 or 4 PCs. So it's not really a wide area, and this can be covered easily by a network cable, right? But what happens when it expands, when we have a wider area that is required to be covered, right? So this is where it now starts to grow. So a LAN is used to link devices in a single office. It could be in a building, it could be in a campus, it could just be in your room, right? Let's say you even have, even nowadays, when you buy a Wi-Fi or rather a router, they come with a LAN cable just in case you have very close proximity to that device. You can just connect to it and enjoy your network, right? But then LAN is usually owned by private small offices or small environments. But this now grows into when we are speaking about a WAN, which is the wide area network. So the WAN is just simply a collection of these LANs. And the WAN, an example of a WAN is indeed the internet, right? So how this is possible is this small collection of networks are all interconnected with each other. And then this spreads across depending on, how far wide the world is. So the internet itself is just a large collection of LANs. So by definition, the WAN is wide area network. That is what the acronym stands for, and it's a collection of several LANs. Network speed is usually less than the LAN, right? Because it is wider. You now have a wider space for it to connect. The network packets need to travel across various hops for it to land at its destination. So by virtue, it is not as fast as a LAN, right? But then it spreads over the world and may spread over more than a city, a country, a continent. And then systems on the network are connected indirectly. It hops from one WAN to the other, and then it keeps on doing so until it lands at its destination. So usually, one network is owned by larger corporations or, bigger networks and operated by network providers, right? Hardly owned by a single entity. And if it is for an enterprise network. It's a network that's very large. So if we're talking about an example would be extended corporate bodies like CBN, the NMPC. They have franchises, they have spread across, but then they all have to be in a separate network. So that is a summary of what the WAN is. And for one word to just describe it, the internet is WAN itself. The next is a MAN, which is the metropolitan network. So the MAN is an extension of a local area network, but mainly spread over a city, right? And maybe a single network or in a cluster of networks. So the idea is they can easily share resources per region, right? So it's like a subset of the WAN. It can be grouped under a WAN itself. So yeah, this just kind of breaks down how networks can exist in either small areas or in larger areas. So how is network provided? You get networks on your system, you get networks on your phones, and all of that. One of the major sources, or one of the most popular and most used sources of network is from ISPs themselves, which are the internet service providers. So the internet hierarchy, right, when it comes to use, availability of access to network is based on what you can see on this display. Starts from, we're going bottom up, right? From international ISPs, where you get fiber cables passed across the sea, and this connects continents themselves. This is the highest tier, and it's what creates the global network as we know today. In some time in the past, there was a cut to one of the major suppliers of this network, and there was a lot of downtime, not just in countries, in continents. So this shows you how important the highest tiers of these network providers are, which is international ISPs. The next is national ISPs, right? This connects regional ISPs, international ISPs. So in summary, from the international ISPs, it goes down to the national ISPs. From the national ISPs, that gets further broken down to regional ISPs, which connect local ISPs to national ISPs. So don't forget, anytime you hear ISP, I'm speaking about internet service providers. And this goes down to local ISPs, and then which eventually gets down to the endpoint system or the endpoint itself. It could be a phone, it could be a laptop, it could be a tablet, whatever device that is consuming that network. But this is the way the network passes before it gets to that device. But of course, with logical setup, infrastructure on ground, content delivery systems, these have become a lot more accessible. Right? Sometimes you get content off of a CDS, right? And it would be able to serve as that. But whenever you are requiring the network functionality, it passes through all of these tiers. So next is one of the very key things to learn in networking is the IP address. I'm very sure at some point you must have heard IP address. So the IP stands for Internet Protocol. And in a simple way to look at it, at its core, is just the address of maybe a certain destination that you're trying to arrive at, but on the network, on the internet, right? So as I told you, the internet itself is comprised of various networks. So let's look at a LAN, for an example. Let's assume you have 2, 3, 4 PCs connected in a small environment or in a small environment, maybe in an office or in a room. So for you to be able to successfully, send information to all of these devices, you need an IP address. Usually the IP address is consolidated with the MAC address, but that happens without you knowing. So on the internet, the IP address is just, like I said, the address of any service you're trying to access. If it's a website, you go to www.google.com, that is just the URL, the user-friendly address. That's the type that you can easily understand and remember. But it's what you call a DNS, which consolidates that IP address and maps it to the actual, it consolidates the URL and maps it to the actual IP address and sends you that destination. So it's a more direct way to send information. So by definition, it's a unique numerical label assigned to each device connected to a computer network that uses the Internet Protocol for communication. So as you can see here, it's like a postal address for a computer in very basic terms. So the IP address, it's in 2 formats currently that exists. We have the IP version 4 and the IP version 6. And we'll discuss more about these 2 types and their differences. But for now, it's just better to understand that IPv4 is the older version, right? And IPv6 was created to address possible exhaustion of the IPv4 address, which in reality has not really happened because of some other frameworks that came to help, further expand the IPv4 address. But to speak more about why this is an issue, right? You can see the next slide here. As I said, the IPv4 is the older version, has some limited address space, and about 4.3 billion of those exist, right? And then the newer version, which is the IPv6, has about 340 undecilon addresses available to be used. So the IPv4, you see, we have 4.3 billion of those, but the world, I think, total population is between 8 to 9 billion people. So you see, that's not very feasible. And then everybody has most people, I won't say everybody, have multiple devices. So you can imagine the amount, as in everybody is on the network at the same time. So it will not be possible for us to effectively navigate traffic. But that's not the case because, one, internet penetration is still not at its highest in all regions in the world. 1, 2. Right now, we have things like DHCP, which is a protocol that kind of automatically assigns IPs for active nodes on the network. So you don't necessarily, and this is recycled, you don't necessarily need to use a static IP forever. Right? So this kind of defeats the purpose of the creation of the IPv6, but not entirely, because we might still get there. But the IPv6 exists and is still assigned, but it's, most of the time when you are hearing IPs, people still very much use the IPv4s. So on the table, you can see there is a breakdown of the IP by classes, right? We're not going to get deep into this because this is an entire course on its own. So this is, you can see that it's broken down into 5 classes. And for each of them, we have like a range of IP addresses that are associated with those classes. Some are very popular because they are used mostly on the open net, while others are secluded for specific, let's say, intranet type of organizations that have very large infrastructures and they want to have their network themselves, which is understandable. especially for financial institutions, core infrastructure, critical facilities, and all of that. But to understand the reason why the IPv6 was created was because of the possible exhaustion of the IPv4. So next is to speak about the TCP/IP model, and we're also going to talk about the OSI model. But first of all, what is the TCP/IP model? TCP stands for Transmission Control Protocol. The IP, as I mentioned before, is the Internet Protocol. And they're known as the IP or the Internet Protocol Suite. And it's the foundational framework for how data is transmitted across the Internet and most modern networks. And it organizes the networking protocols in 4 distinct layers, right? And on ground, practically speaking, the TCP/IP is still the model that is recognized and it's still used mostly. But we'll get into the OSI model and I'll tell you how it is different or like an augment. So it enables devices to communicate reliably and efficiently, but distinctively breaking them into these layers. So if you want to troubleshoot, it's easy to know what layer you're troubleshooting from, because it's like I said, networking is quite deep. It goes really deep. There are professionals who are solely focused on networking, and this is like an entire career building off of that. So for the TCP/IP, you should just know that there are 4 layers. The network access layer, which is layer 1. We have the internet layer, then the transport layer, and then the application layer. Network access layer, internet layer, the transport layer, and the application layer. So before we get into the OSI model, I want to kind of like break down what a TCP handshake is. On the network, for there to be a successful communication, there has to be a TCP handshake, right? And the TCP is a 3-way handshake. It's a fundamental process used to establish a reliable connection between the client, which could be your computer or whatever is requesting that connection, and the server over the network. So this happens in 3 formats, which is as you can see, the sign arc, and the arc. So first of the client device sends a SYN request, and then it is, if the server is up and running, it replies with a SYN ACK, synchronizing stroke acknowledgement, and then the client device also now sends back an acknowledgement. And then this now establishes a secure and reliable connection. So this way, the client device knows that the server is up and running and it's ready to interact. Okay. So now, let's delve into the OSI model. But before I do that, let me go through the chat to see if I have questions. Okay. No questions so far. All right. So the OSI stands for Open System Interconnect, or Open System Interconnection Model, popularly referred to as the OSI model, is a conceptual framework that characterizes and standardizes communication functions of a telecommunication or computer system without regard to its underlying structure and technology. So this is like the TCP/IP model, but further broken down. The OSI model is more of, let's say they use it more of when troubleshooting, to narrow down where the problem is or where you need to troubleshoot from. So some of these layers of the OSI model are further compressed into what you find in the TCP/IP model. And I'm going to demonstrate that with some visuals going forward. But the OSI model comes in 7 layers, right? And as you can see, the layers are arranged. There's a very popular mnemonic that you can use to remember the OSI model. which is the please do not throw sausage pizza away. And then that kind of like speaks to all of the layers that you see. So starting from the key, please, physical layer. This is where you have the actual physical hardware connected here and there. So the physical layer is the layer that you can see, feel, and touch, more or less. And then we have the data link layer, which is often referred to as layer 2. So the layers are numbered from layer 1 to layer 7. When you hear layer 1, they usually speak about the physical layer, layer 2, the data link layer, right? And then we have the network layer, which is the next layer, the transport layer, the session layer, the presentation layer, and the application layer. So to kind of refer this to the mnemonic I gave you earlier, please do not throw sausage pizza away. Please is for the physical layer. Do is the data link layer. Not is the network layer. Throw is the transport layer. Sausage is the session layer. Pizza is the presentation layer. And then away is the application layer. You can use this to easily remember the layers in case you want to go forward with understanding it better. But I'm going to tell you, I'm going to break down what each of these layers do and how you can understand where a problem is if troubleshooting from a networking perspective, or just trying to understand how things move on within a network, right? As you can see here, the physical layer, you see what is roped under that is the Ethernet cable. So that is a physical, actual thing. So the Ethernet cable, like I mentioned before, is usually an RJ45 cable, and this is the kind of cable that enables networking between two devices or enables two devices to be able to communicate. So that's for the physical layer. For the data link layer, is we have MAC addresses and switches, right? Because on this layer, you are able to see MAC addresses. There's a MAC address table. A switch also operates at a data link at the data link layer. So when you hear it's a layer 2 problem, it's most likely associated with these things and others. Then the network layer, so you have IP addresses, routers, or they're what you also call network enabled switches, which more or less function on the network layer as well. So these are all part of the layer 3. So layer 1, 2, and 3 are very much spoken about, right? Because as from a networking perspective, you're trying to troubleshoot most of the time. These are the 3 areas where you need to look at. Then we have transport layer where you see you have the TCP and the UDP, which kind of is a protocol that addresses how these packets are, sent and how they are delivered. UDP doesn't necessarily ensure packet delivery, but for the TCP, it ensures that. So these are areas that you can get deeper into, but for now, I'm just trying to give you an overview to understand what the OSI model is. Then we have the session layer, which kind of like monitors sessions to make sure that there are no clashes or collisions, and each session is on its own and it's complete without any interference from other sessions. Then you have the presentation layer, which usually has encryption done on this layer, right? Encryption and decryption, the sender and receiver is done on the presentation layer. And the application layer is now more like the layer that is, directly interfacing with these applications that are disseminating the information that has been sent. And one of the very capital examples for this are web browsers, right? So these are, it's like let's say, minor introduction into the OSI model and each layers and how they operate. So like I mentioned before, this now also kind of like gives you a more, let's say, pictorial understanding of each of these layers and how it communicates. Right. So for the physical layer, you can see the layers are directly connected to the next layers and not they don't jump. You cannot skip a particular layer when the transmission is happening. you can see from device A to device B, you put out, you have intermediate nodes, which could be networking devices, maybe your routers, or your network-enabled switches, or you have local area networks in between where you have device A or device B. But this is the hierarchy at which the information is going to pass, right? So also starts from the physical, you can see the data link in the network. Then, like I mentioned, these three are the major pain points of network engineers, because this is where they spend most of the time. But then when it exceeds this, it goes on to the network, and then you see transport, session, presentation, and then the application layer. Okay, so now we kind of like, this slide kind of breaks into the TCP/IP model and how it is different from the OSI model. So the TCP/IP model was developed before the OSI model. That has been in existence since the 90s. The OSI model was in the early 2000s. Right? The TCP/IP is a set of protocols, as we discussed before, developed to allow operating computers to share resources across a network. So it is an open protocol standard, freely available. It is developed independently from any specific computer hardware or operating system. So back in the days, it was difficult for separate companies because then each company had a certain way that their own computers were communicating with each other. Things like then we still had APRANET. So the TCP/IP model was very instrumental to intercommunication between different PC makers and the way their information was able to be shared. So before it wasn't possible, just like before Apple PCs could not send to HPs, right? But now that is no longer the case. And the TCP/IP model was the foundational model that made this possible. So a common addressing scheme was necessary to enable to connect most widely used networks, right? So it connects dissimilar systems and it provides a client-server framework for any type of connection. So now to look at the difference between the OSI and TCP/IP model. TCP/IP model combines the presentation layer and the session layer into the application layer. Just for reference, you see the presentation layer and the session layer are layer 6 and 5. So that is compressed into the application layer. You can have right? So all of this is the application layer for the TCP/IP model. Then next, it combines the data link and the physical into one layer. As you can see here also, that is the physical network interface of the TCP/IP model. The next, it also appears simpler because it has fewer layers, just 4 layers. And it is, as I mentioned before, it's more practical on ground. But also, you can see that TCP, the last point here, we have the TCP/IP transport layer. This is UDP and does not always guarantee reliable delivery of packets. But the transport layer in the OSI model does. Basically, the OSI model kind of addresses this issue. But I told you OSI model is a newer version. So obviously, it's going to issues that were very apparent with the TCP/IP we are solved on the OSI model. But based on what you can see, the application layer, as we said before, is a combination of the application, presentation, and session of the OSI model. The transport is still the transport, and the network layer is the network layer, but then the physical layer is a combination of the data link and the physical layer on the OSI model. Okay, next. Now we're getting to delve into VLAN. VLAN stands for virtual LAN. And as we know what a LAN is, which is a local area network. So at its core, right, VLAN is simply segmenting a physical network into multiple logical networks at layer 2. So by saying this alone, you should know that this would most likely be done on a switch because a switch functions at layer 2. So that means that it maps the ports. And when I say ports, I'm not talking about the network ports. I'm talking about the actual physical ports that you have on the device to certain MAC addresses, and it's able to now logically segment the network. So let's assume that we have a room and then we have 10 PCs connected. So with VLANs, you are able to segment some certain PCs to be able to communicate with each other and not see the other ones. This is efficient when you have a small enterprise or a small office, and you obviously would not want the guests to be able to see, or let me not even say guests, random members of staff to be able to see what HR is doing or what finance is doing. So this is a very good example of where VLAN comes in. So it isolates broadcast domains and improves security and efficiency, because every corporate body, or for whatever reason that you need to segment your network, it is possible with a VLAN. So how do VLANs work at their core? The devices on the same VLAN can communicate as if they are on the same physical network, right? Even if they are physically separated. So if you have a large organization and then it has, let's say, 10 floors, and each of these floors are separate, but then you have a very huge networking infrastructure, you can put all of some certain, maybe departments on one VLAN, and they'll be able to see each other regardless of the fact that they are far apart. But then the ones that are close, you can still segment them in a way that they don't see each other regardless of the fact that they are close. So the main thing to remember here is logical segregation of the network itself. And the switches assign ports to the VLANs, routes, firewalls, and they manage inter-VLAN traffic. To be able to configure inter-VLAN, you would require a network-enabled switch or a router or something that can be on the network, because it is on there that you can now can configure inter-VLAN traffic. So that would mean when you want these VLANs to communicate, you are able to do so. And when you do not want that to be the case, you are able to do so as well. Okay. So these are like some of the extra, let's say, attributes of the VLAN in terms of their structure. So the core network segmentation is the VLAN itself. It happens on layer 2. Layer 2 segmentation divides the network at the data link layer. Then there's broadcast domain isolation, which prevents broadcast traffic spread. And we have improved security. Why? Because you're enhancing network security by segregating the kind of traffic that passes to where, and basically redirecting or, let's say, caging your network to be where you want it to be. And it's efficient because it optimizes network performance, more or less. So this is like an example of a typical implementation of a VLAN, right? Where you have, for instance, like I said, an organization, a small one or a huge one, have a sales department in a different VLAN, a marketing department in a different VLAN, the engineering department in a different VLAN, and also the HR department in a different VLAN. So this kind of, as we said, at its core, it helps enable network security through logical segmentation. So another good network security implementation is the DMZ, which stands for Demilitarized Zone. So DMZ is a subnetwork that contains and exposes external facing services such as web and mail servers to the internet while isolating them from the internal network. So typically, let's say organizations or individuals who have, let's say, public facing type of services that's going to require a lot of interaction from the public, and then you want to segment that entirely from your internal network, the DMZ is more practical for you. How it works, so typically it's positioned between two firewalls or between the firewall and the internet, right? And you can now specify what traffic you want. Some people would say DMZ is just an overhyped type of firewall, but no, it goes deeper than that, right? So when you do these specifications, just as mostly how you do on the firewall or on an ACL, internet network access from the DMZ is tightly restricted. This is on basically for security reasons. Also, some attributes of the DMZ traffic as well, as you can see on here on the screen, is one, secure and private network. There's a buffer zone for public servers. So we have the firewall also still working. That's a very important component of the DMZ, which serves as the main security barrier protecting the networks. And then the internet itself, which is the global network connectivity, and that is where you have the public access coming from. The DMZ, ensures security while all of these are still in the interplay. So there has to be a balance whenever DMZs are being implemented, right? You're looking at specific traffic allowed and tightly restricted access. There has to be that balance to ensure that availability is there. Because in any security framework, you need to consider three things: confidentiality, integrity, and availability. If any of this is trampled upon, you are infringing upon cybersecurity and also by extension network security. To have specific traffic allowed and then tightly restricted access. The balance is at its core where the DMZ is most efficient. Okay, now getting into the last part of the theoretical aspects for networks, talking about zero trust network security. So with the way things have evolved and with the way networks have been infiltrated, threat actors have developed more efficient ways of infiltrating networks. The zero trust network has been gaining more popularity. So I think in the last 5 years, it has become more important than it used to be before. So before, it's mostly critical infrastructure organizations that leverage the zero trust network, right? Because of the amount of, I won't say stress, but to a layman, it's quite stressful, right? With ease comes vulnerabilities. That's one key term to remember. So the zero trust network is a security model that shifts from traditional perimeter-based approach, where everything inside the network was implicitly trusted. So usually, if you are on the network, if you're a trusted device, you have a lot of access to a lot of things on the network by default because you're a trusted device. And this typically has become a problem, especially when you think about insider threats. Insider threats have really been a serious issue, and zero trust network kind of addresses that at its core. So instead, zero trust network assumes no user or device should be trusted by default, regardless of your location, even if that's where you sign in every day from. Doesn't matter. Inside or outside the network perimeter. It emphasizes continuous verification and strict access control. So one of the key terminologies or say key phrases that summarizes what zero trust network is trust but verify. Trust but verify. So we're not saying you're not the person you're saying you are, but we need to verify again and again. So this is currently, if you are maybe handling any administrative console on any of the big techs, maybe Google, Amazon, and all of that, usually you see prompts and requests for you to re-verify your identity, even if nothing has changed in your network infrastructure, you've not changed your IP or whatever, you've not changed your device. It just requests that to be done because it understands that you are using a core account, an account that has access to do a lot of damage. So if you are the person, you should actually have security at its forefront or at one of the main things that you want to prioritize at all times. So zero trust security is very, very key. So as you can see, three things outlined here: identity verification, confirms user identity at all points in time. Device verification, apart from the user using this device, just because you use it 100 times doesn't mean we trust it. So there's that device verification as well, because as we know, nowadays spoofing has become way easier than it used to be. And, that kind of defeats the whole point of having security. Then least privilege access, right? The principle of least privilege is always implemented. And the principle of least privilege simply states that give access to what is required to perform a role or a task. Do not give more, do not give less. This is actually a very important component that I believe should be even implemented in your life. You don't allow everyone have access, just like that. You give access to the level that is required for that person. So there is no use for the IT in the organization seeing what is happening in finance. Right? Why? So you might feel like, oh, at some point you might need to do something here or there. And the IT has signed an NDA of this and that. The main thing to consider is what about if that person is compromised unknowingly? And then the person has access to all of these things. So you see, you are more or less digging a grave for yourself. So if the person shouldn't have access, because the person doesn't necessarily need those resources to perform his daily functions, his or her daily functions, then it's not necessary to give access. Zero Trust emphasizes this and makes sure it is part of its architecture. So another way to look at this is Zero Trust can be applied to data access as well and the management of data at its core. Right? It brings about Zero Trust data security as well, where every request to data or access to that data needs to be authenticated dynamically and to ensure least privileged access to the resources. Very important. So we can see a pictorial breakdown of how Zero Trust will function. Right? First off, you have two individuals trying to access some resources. One is from a trusted device and a trusted personnel, the other one is not. So this entire place is what we can refer to as the data plane. We have the policy decision point control plane, the policy engine, policy administrations, right? And all of these directly into policy enforcement points. So the resource, as you can see, is kept at the far end, right? You now have various accessing points or points that you would refer to as places where naturally you would have implicit trust. Like if you're in the HQ, the headquarters of your office, nobody expects that you're a malicious actor. If you're in your branch office, or if you're in your home, where you usually, maybe if you work from home and you usually access office resources from there, maybe the data center itself, public access or VPN access. All of these do not have implicit trust. Implicit trust is not placed on them at all, right? Secure communication across any infrastructure is necessary, but still, implicit trust is not given. They are all blocked unless all of the policy enforcement points for the Zero Trust architecture is met. Right? And as all of this is happening, you will need to scale through all of the, like I said, policy enforcement points before trust is issued again. And you can now have access to either the company's internet, its softwares, its database, data centers, basically its resources. As this is happening, we have active also background policies that keep non-repudiation in check. So there's activity logs. We still have threat intelligence on the SIEM and the SOC side. We have industry compliance, making sure that you are in check with your GRC. We have CDM systems, SIEM systems, ID management. SIEM is the security information event management. We have public key infrastructure, and we have data access policies. All of these work together to create or to further curate what the zero trust policy and zero trust architecture of the network should be like. Okay. I hope that clearly breaks down and explains everything that's required to know on the theoretical aspect. So now we want to delve into the hands-on session. And I would like to direct everybody to go to your Hack365 Global portal and access the networking lab there, which is on the beginner section of it. Let me see. Mhm. So let me go back and show you how you can. When you go to the Hack365 Global, you sign in. So when you're signed in, all you have to do is go to the beginner section here, and you scroll down to networking fundamentals. You see the Cisco packet tracer, then you click on play. So this is a beginner friendly lab. So should be pretty straightforward. The lab objective, as we can see here, is to learn how how to use Cisco packet tracer to design and simulate networks. So the purpose for this would be to allow users here to create virtual network topologies and configure Cisco networking devices. So the tool will be using is packet tracer, as I mentioned. A very easy way to get access to this, which you can see here in the lab prerequisites, would be to visit the Cisco Networking Academy website and either register for a free course or just log in. If you're already registered, you'll be allowed to access the download section, right? And then just choose the version that is compatible with your operating system, if it's a Windows, if it's a Mac, or if it's a Linux-based operating system. Then when you have that done, you will get started. Okay. So first things first, when you have the Cisco packet tracer downloaded, then you have it fired up like this. If you're on the Mac OS, yeah, there has been some recent issues I was noticed. It always, whenever you fire on your packet tracer and you have your network on, it keeps on requiring you to, it will keep on requiring you to sign in. And sometimes the sign in would not allow you have access. I think it's an issue on I don't know, maybe their side. So a little way to get around that would be to turn off your network, open Cisco Packet Tracer, and then you can turn it back on if it's necessary. So when you open up the Cisco Packet Tracer, one of the most obvious things you see is the white space. This is called what's called the logical workspace. So we have a lot of other things that are around, right? So Cisco Packet Tracer, as you see here on the lab, is a very powerful network simulation tool. We can use it to, you know, simulate networks. You can simulate LANs. You can simulate as you can simulate WANs. You can simulate complicated networks. You can. It just gives you an one, let's say, stop shop for almost everything you want to try out with networking, right? It's quite powerful. I think the other alternatives to this would be GNS3. GNS3 is also quite a good tool. But yeah, on the Cisco Packet Tracer, whatever you can do there, you can do here as well. So first off, let's go to the tools we have here. You can see top we have a series of menus here, and if you hover over them, you kind of get like a brief, you know, description of what that tool is. So we have the new, this helps simulate if you want a new file, if you want a new logical space, and just hit this new button, and then you have that. And you can save directly from here. You can open an already saved file. Then you can decide to maybe save in a different manner. You can print what you have on your screen. So you have a series of, you know, menus here that would come in handy when you need them. And if you're a bit confused about what that particular tool does, you can just hover over it and you'll see a short description of what it does, right? Then just below it, you have some other, you know, functional tools you can use to either inspect, delete, select, expand. You can place notes, you know, on certain areas of your network just to give you like a brief explanation of what is happening there when necessary. You can draw shapes and forms, and then you can also use a PDU. PDU is a protocol data unit, which is kind of like used to see how packets move within the network, right? So when you ping an endpoint on your network, you're able to see how that flows through the network. And from that, we are going to understand more about the network itself. Then you can see the logical space, you can click to the physical. If you click physical, it kind of like gives you an actual breakdown of what a physical environment will look like. Right? And then you can zoom in and zoom out and all of that. You can decide to add things from here. You can create your own buildings. You know, you can do a lot of stuff. And then we're going to be, you know, getting hands-on with it. But for this lab, these are not necessary. Go back to logical space. So beneath that, beneath the logical space, the first line that you see there are, let's say, grouped devices or grouped utilities that you might use to, or that you will use to create any type of network. So first off is the first thing that you see here are the networking devices, right? And as you click on that, just below it, you see it's like a folder, and then it opens up some other things. You have routers categorized, you have different types of routers here. You can scroll through to see maybe if there's a specific type you're looking for more advanced engineers or people who actually are already, you know, already have knowledge of networking. You can scroll through there. Then you click here to show you all of the switches that you have available here as well. The next is a hub, and you click to show you what we have there for hubs as well. And see, we can also put in wireless devices. See all of the ones we have available here. And also security. We're looking at having different type of security devices also implemented there. Then to also simulate cloud environments, you can use, just hit on the cloud one emulation here, and then you would see all of this. So based on our lab, we have about 4 tasks here to perform. The first task is to establish a P2P connection, just point to point between 2 PCs, right? So to do so, you just can easily follow the steps and you'll be able to successfully do so. And we need to answer one of the questions that we have here, right? This is just kind of like lets you know that you are on point with what you're doing. So we're clicking and bringing up 2 PCs of logical workspace. We are connecting them with a cable, and then we're assigning IPs to both of them. We navigate to the CMD on each device and ping the other just to verify connectivity. And we can do so by pinging the IP address. And do not forget, the IP address have been provided. We have 192.168.1.1 and 192.168.1.2. So let's get on with it. So first off, what you need to do is to click on your endpoint devices. As you can see, I've done so. You can either decide to use a normal desktop PC or it shows you all types of connections available, right? You can also get this if you're on HP, and you control alternate O, and then that opens up that. When it is on Mac, you use command control shift O as well. That should work. Next here, as you can see, the next is to connect both using a copper crossover. So there are 2 main type of connections you would notice. Main, I didn't say only. So the copper crossover and the copper straight through. Right? The copper crossover is when you're connecting 2 devices of same type. But then the copper straight through is when you're connecting 2 devices of different types. Let's say you're connecting an endpoint device to a network device. You would most likely use the copper straight through. If you're connecting the endpoint device to an endpoint device, like this, what we're trying to do is a copper crossover. So all you have to do is, if you hover over this one here, that's kind of like a broken line, you click on that, and then click on whichever PC you want to click on, whichever the first PC that you want to connect to the other. It's going to show you all of the available ports on that PC. Right, as you can see, we have USB ports. We now also have the fast Ethernet ports, which is what we'll be using. So Cisco Packet Tracer kind of like simulates an actual, as realistic as possible network connection. So if you are actually to connect 2 PCs, which has an RJ45 port, as we are seeing here, the fast Ethernet port, you know that, oh, this is where you need to connect it to. And now we click on that, it has connected to the port, and you can see that the wires are like, extending to show you that, oh yeah, it is now connected. And you click on this part as well, and then it will bring a drop down of all of the available ports as it did in the previous one. And you click here. So automatically you can see that there's a green indicator here showing that, yep, we are connected and we are available to communicate, right? So just for emphasis, I'm going to show you connecting with the wrong type of cable and what you'd see. So for these other PCs, you are still supposed to use a copper crossover, but I'm going to use a copper straight through just so you see that it will not work. All right. You see, I've connected these 2 PCs, but you can see directly there's a red indicator there. So there are 3 colors you mostly notice while working on Cisco Packet Tracer: green, the red, and the amber, or I call it orange. So usually when you see green, connection is up. When you see red, connection is down. When you see amber, it is deciding, or it is learning, or it's in the process of, switching. So as we go on with the lab, you would come to notice this. So now, the lab requires us to create two IP addresses, or rather configure these PCs with the required IP addresses. So to do so, we click on the PC itself. So as you have clicked on the PC, it is first of all giving me a pictorial view of what an actual PC of that nature looks like. This is a CPU. And for those of us who have used this type of devices in the past, you would recognize it almost immediately. You can zoom in, right, and then see the PC itself. One of the fun parts I like about Cisco Packet Tracer, something that I got excited about while I started using it, is the level of detail that they put into it, right? You see this device now, as you're seeing it here, I can turn it off by clicking on this red button, and then this PC is off. And how can we tell? Because it's off, you can see it's kind of grayed out, and then the connection is no longer active, it's now red. As I told you, when you see red, it cannot communicate, right? So that's one thing that is there to note. So put that back on, you can see it's back up green, right? Then we go back here, and then we go to over here, up of the top here. You can see that we have about 5 different things we can select. We have the physical, we have the config. So the physical shows you the physical aspect of the device, right? You can see all of the ports, the USBs, and where you put stuff. Then the config is if you want to configure a certain part of it. We can directly configure the IP also from this area, but this is where it is. When you click on the desktop, it shows you all of the services you can access via the PC itself. So this is like you've turned on your PC, and then you can see some of the utility features that you would find on a regular Windows PC. So now we will go to the IP configuration for the configure the IP. We're going to be configuring the IP version 4 address. And based off of the lab, we have to use what 192.168.1.1. I'm correct? Yeah. And if you notice, the subnet mask is automatically generated for you. So we have 255.255.255.0. Now this is done. So next, we have successfully configured the first PC with its IP address. So now we can cancel this. We can go to the next PC. Opens up again. Same thing. We go to desktop. We go to IP configuration and put the second one 192.168.1.2. Do not forget, 2 PCs on a network cannot have the same IP address. It won't even allow it. Let me give you an example. Let me put one and then you see what happens. No, this address is already used in the network. So you have to be very careful. 192.168.1.2. Automatically, again, we have the subnet mask generated. So we can now go back to our logical workspace. And to kind of, verify that, okay, this is done, you can hover over your PC like this, and you will see some information about it to be brought out, mostly network-related information. So you can see that the fast Ethernet port is off. Let me hover again. If you look through the information provided, fast Ethernet is off, and the IP is there, 192.168.1.1. And here also, we have the same thing, 192.168.1.2. So, okay, all these are the configurations for the PCs. Let me come to them. It opens up a separate window. So when that is done, now we need to ping to just verify connectivity. Right? So to do so, we just go to the command prompt, and then you do so by clicking on the PC, going to the desktop, and then clicking on command prompt. So from here, let me try and zoom in so you can see. Not properly zoomed in. I'll zoom in. Okay. So all you can do is simply type ping, which is ping, then 192.168.1.2. So I'm pinging the other PC from this PC, right? And ping is a command that is used to check, connectivity to make sure that the destination is up, right? So ping is just simply trying to verify, hey, are you up? Can I communicate with you? So when you ping, you see you get replies. Let me try and make this huge, a little bit bigger. Let's see the view. Let's see command shots. Okay. Okay. So as you can see from the reply, you see we have reply from 191, but we have usually a, a basic thing command usually does four requests. It sends out four requests and then it gets a reply. If it gets a reply, that means that it is up and running. It can actually communicate with that destination, right? So the ping statistics, you see for the ping statistics right below the reply. You see packet sent 4, packet received 4, lost 0, meaning you have successfully, configured your PCs correctly and they can communicate with each other. That's what this signifies, right? So you can go back to our logical workspace. Okay. Problems. Everything is off here. Okay. Okay, so I think I have a little bit of an issue here, but let me quickly rectify that. Okay, the Zoom. So it was, yeah. So earlier I was trying to zoom in for you to see my command prompt properly, but it was zooming the main logical workspace. So now, as you can see, we have been able to do this for these two PCs. And to answer the question that we have here, right? What is the subnet mask IP address, which is automatically created after configuring these IPs above. So to verify that, just go to where we configured our IPs, right? Which is here. Just go to your desktop, go here. You can see this 255.255.255.0. So that's the subnet mask that comes from that is usually should be what should be the subnet mask for this IP based on the range that it falls under. Like I said, IP addressing itself is a very huge topic. And to understand IP addressing, to understand subnetting, and then understanding all of these terminologies, it's a deeper dive into that topic. But for now, this is sufficient for you to practice these labs, right? So that's the first task, which is done. Second now is to, put up 4 endpoints of 4 PCs on logical workspace, arrange them in a star shape, like a cross sign, and a hub in the middle. So a hub is a device which we are going to use right now. Then we connect them to the hub, the copper straight through cables, and then we assign IPs to all PCs, totaling 4. Then we navigate and ping to make sure that we have configured each PC correctly and they can communicate with each other. Right? Then we're going to inspect the event list and traffic flow to see how this is actually happening in real time. So back on the workspace, let's do that quickly. So to be able to select multiple things from your workspace, you can use either, if you're using a Windows PC, you hold down the control button and then you select what you want to select. So what that does is it helps you, not require to go back and pick it one by one. Because usually if you do not press the control on Windows or command on Mac while selecting, you would have to do it one by one, which can be strenuous and stressful and unnecessary. So with that, we're able to position all of the pieces as you can see here. Next is to bring in the hub, right? And we can find out by clicking on network device here. You see the first one is switch, the second one is hub. When you click on hub, okay, no, mistake. So deleted that. So now we have the hub here. Click on select, then put the hub right in the middle. So now we want to connect all of them, right? So click on the connections. And then there's another trick to connecting multiple things, quite easily, right? And that's by clicking on this automatically choose connection type cable here. It also looks like the main cabling for the cable menu. So what you can do here is also hold on command or control, then come to your logical workspace and connect all of these PCs to your hub. So just to give you some basic information of a hub is more like a repeater, right? It does not have any intelligent function. What it does is whatever you send to it, it sends to everybody. So it was quite popular back in the days when internet networking devices were not very popular. So if you have, let's say, 20 people working in an environment and you want to send your person one, you want to send to person five. If you send to person five, the hub will send it to everybody. And then everybody would see what you're sending. So I think the hub is still functional and useful for, let's say, if you have group type of functions that you want to perform. And then you want everybody to get information on what you're doing. So whenever you send to the hub, it distributes every device connected to it. So the hub works on layer one. Yeah, not on layer two. It has no logical addressing. It broadcasts every um, network information sent to it. So more or less, like I said, it's like a glorified repeater. So now next action to perform on this lab is to assign IPs to each PC, starting from 10.10.10.1 all the way through to 10.10.4. So let's do that quickly. IP address of 10.10.10.1. So this, maybe you put that, you click outside of that, you're done. Then that's the first one. Oh, sorry. Next is 10.10.10.2. Next is 10.10.10.3. And next is 10.10.10.4. Okay. So now that we have all of them configured, just to confirm, you can hover over each of them to just make sure that you can see that they have been configured. All right. Excellent. So now we are going to try to ping one PC from the other. So we can go to, this is 10.10.10.4. We'll ping 10.10.10.1 from here and see how that works. If that is up. So let's ping 10.10.10.1. And then you can see we're getting replies, no packet loss, no packets. So it was a successful ping. But just to show you what an unsuccessful ping would look like, let me try pinging. But this time around, I'll ping something that's out of our IP range that we've configured. Let's say .8, 10.10.10.8. All right. You can see request timed out. Request timed out. Timed out. Timed out. And then you can see from the ping statistics below, we have that the packet sent for received none and lost 4. So there was 100% loss on this, meaning that it was not a successful ping, right? So this just kind of gives you an example of what you would see if you do not, or if you're pinging what is not accessible on the network, right? So for this area, we've been able to verify that with our connection, our PCs or the endpoints are connected. And we have verified that by pinging just 2 of them. So to do so, to just further extend our assurance, let's ping from another set of PC. We have this one, we can ping 10.10.10.2 from here. Ping 10.10.10.2. And then you can see it is successful. Ping statistics show that we have 4 sent, 4 received, and none lost. So for a successful ping. So now you can see that all of the devices connected are efficient and they are seeing each other. Another way to, because the lab also specified that we confirm using the event list, right? So to access the event list, it can only access that from simulation mode. When you click on simulation here and you come and press play, you would see it in real time. Let me go through that again. Let me ping it again, then we can see it in real time. Ping, let's do 10.10.10.3. Let's do 10.10.10.3. And we verify that that's on there. So we go back to simulation mode now. We see how that is working, right? And to get more intel on this, we put out the event list. So the event list, it's like a log of every activity that is going on in the logical space as it is going on in the logical space itself. So now that because it's a hub, as you can see the flow of traffic, right? The PD goes to the hub and then it distributes to everybody. Right? See, the two cancellation shows that this is not the actual right addresses. This is the right address. This gives a confirmation. And you can see that the protocols that are being used are also displayed. We have the ARP, the address resolution protocol, which the hub is trying to understand the addresses, even though it doesn't necessarily save that information or it helps to do anything. But once it verifies that this device is here, it now starts sending the ICMP type of messages itself. But from the devices that are making these motions, you can see them here as well as it is happening. And if at any point in time you want to stop the simulation, I just press pause here. You can move back to real time, right? And just toggle in between both of them to verify at every point in time. Right? So next is to, we cancel these ones that are already open. So we ping them, ping the IP address, we send the email, we observe the traffic flow. We've completed the second task for the lab itself, right? So for the third task, it's something quite similar, but we're using a different network device. And the idea is to show the difference between what a hub would do and what a switch would do. Like I mentioned, the hub still works in layer one, and it does not have any intelligent function. But the switch has some sort of, intelligent functions when compared to a hub because of how it is able to, implement logical addressing. It has a MAC address table, which it now assigns the ports to the MAC addresses of the devices that are on the network. So I'm going to do so by, you can quickly delete this. Let me see. Now I'm going to drag 4 endpoint devices again to the logical workspace. 1, 2, 3, 4. And then I'm gonna put a switch in between. You can use the 2960, which is fine. Oh, that mistake. You can use the 2960 switch and put it right in the middle here. And don't forget, if you want to adjust anything on your logical workspace, all you have to do is click and drag. Click and drag, all right? So now is to establish a connection between them all. Oh, I should have. Command. Right, so as I mentioned to you earlier, you can see the amber on each of the ports connecting to the switch. Kind of lets you know that it's still, learning. The switch is still trying to familiarize itself with the devices connected to it because it does so automatically. All right. So now we are going to assign IPs to all of them as well. Let us get to the lab itself to see the requirements. So we're going to assign IPs from 10 to 10 to 5 through to 10 to 10 to 9, right? Total of 4. Let's see, 4 IPs. Okay, we'll start from 6 to 9. So we'll have that in the star shape, kind of explain the topology. All right, so on this section, it's similar, like I said, to the last task, but this time around we're using a switch. So we now assign IPs to each one. We have 10.10.10.5. Next is 10.10.6. Next is .7. And then .8. Right? And then all of them have the same subnet mask, if you notice, automatically generated. So once you've done this, and close all of those pages, because for every time you select any of those devices and it opens up, Tracer opens up a separate window for you to do so. So now that all of them are configured, you can hover over them to ensure that they are consistent with what is required in the lab. So we have the 5, 6, 7, 8. All right. So now we ping from one to the other. Ping, send out, send out, send out. Let's do it. Just make sure it's there. To make sure it's there. So now let's now simulate this and then see how it's different from the hub itself. When we go back and play, you can see what's happening. First of this, the switch learns the address for the destination that it's supposed to send to. And up when it did that, subsequent broadcast would be specific. Right? Now let me show you how that will be done. Now let's go from this one and ping.5. Ping 10.10.10.5. Wait on simulation. Simulation mode is usually slower than the actual mode. You see, each and every packet was sent, each was received. We had none lost, zero lost packet. So now let's simulate that to see again. Let's do the ping again. Make sure that we are on the same page. So now we are pinging directly, and from the event list, you can see that it is moving directly from PC9 to switch 0, from switch 0 to PC8. Right? And then back to switch 0. And it keeps on doing that. But one of the clear differences that you would find, right, is that with the switch, immediately it learns the address. It does not send any broadcast domain anymore. In fact, when it starts out, it learns the address and then it directly sends the traffic specified for that destination IP without any other, broadcast, just as the hub was doing, as we demonstrated before. So that's one of the main differences between how a hub and a switch functions in any network architecture or any network topology. So the switch would give you more logical, more smarter functions than a hub. A hub is just a glorified repeater. So we've tested connectivity, and I think we are all good. Now we are on to the last task on this particular lab, right? And what we need to do here is to create two clusters. So what a cluster is a combination of network devices on one particular, ontological workspace. Network devices all connected to one, endpoint devices all connected to one network devices together in one area. They can define it as a cluster. So here, the clusters we have are to contain 3 PCs and 1 switch, right? And these switches are to be connected to a router, right? So there's going to be some required configurations on both sides to make this easy, right? So now, first of all, we need to create these clusters and connect them just as just as been requested or outlined on the lab itself. Let me stop this. Uh-huh. So here we have .7. We have an issue here. We did on simulation mode, that's why. It's not set, but issue .6. So we now have it at .6. This is .7, it should be .8. .8. There should be one more. Let's say .9. Oh, 3 to 6. .4. .5. .6. Need to add one more PC here. And here as well. So here we have .8, then there'll be .9. Yeah. Okay, yeah. So we have got from .3, 4, 5. It should be 6. It should be 6. Right. Then the other area, the other cluster. So this cluster 1 and this cluster 2. So how can we easily identify that? We can do so by drawing something, let's say an ellipse around it. And use, if you click on this particular tool here, it's like a palette dialog comes up. Then you can draw shapes around just to like show different connections or different types of, just to show a difference between something and something. Here's the fill color. Yeah. Okay. And Now good are here. 1, 2. Now let's change this. 2. So we now have 2 different clusters. But one said is fill color. We have to do this too. So we can have a fill color. Let's see if we can have that done easily. Let me do it this. Okay. So now another thing that will be very helpful to easily remember our IP ranges is to use what you call this. What's that? This is a note. You can place a note anywhere on screen. It's misbehaving. Sorry, I have some misbehavior here. Okay, something is off here. Now that we have them connected, right, without wasting much time, let's just get into configuring the router itself. On the router, first things first, you need to understand which particular port is connected to. So we have the gigabit port. We have 2 different types of ports, the fast Ethernet and gigabit ports. So the gigabit ports will take up to 1,000 megabytes per second, but then the fast Ethernet ranges from 100. Yeah. So on the router, you would find that to configure it, when you click on it, you go to the CLI. So here you might just need to type a few commands. So first off, you're going to be greeted with an information for initial configuration dialog. Just type yes, or rather, just to know since we are doing this ourselves. Uh, Let me restart this. We have a problem here. Okay. Let me redo this again. Uh-huh. Google password. Okay. I'm thinking we're having some slight issues. Let me reconnect the router. Put this here and then enable the connections. And now we configure it again. So we'll let it boot up. And just take yes. Right. The host name, we have it to be router 1. This should not be. Okay, so sorry. Should have zoomed this in. So the issue we're having is the configuration dialog box. This can help you configure your router easily if you're not used to doing so. But we do not need to do this right now so as not to waste our time. We can just directly have it by doing this. Okay, now let's go back here, forward time. Click on our router again for configuration. Go to the CLI, ask let's just do no. Excellent. So we don't need to do we don't need to activate the configuration dialog box as we were trying to before. So when you get into the router, the first to type is enable or EN for short. Then that gets sort of the user global mode to the user executive mode. Then from here, you type to configure the terminal itself. You type conft. That opens the configuration area for the router. So next is to try to put up the interface that is connected to the router. So we have two ports that the router is, that has the connection to the router. The gigabit interface, you can find out by hovering over the connection itself. And then the other one is also what? Gigabit interface 0001. So how we do that from here is to we don't config, then we type interface, then we write the specific interface we're trying to configure, which is G0000. That's the first one. And it switches from configure to configure interface. As you can see, config IF means configure interface. So right now, we're configuring the interface itself. So we can add the IP by making sure we put two things. First off, we go to this area. First off, we type the command no shutdown. This brings up the that particular port to be now active. So before it was not active, but the no shutdown command just put it up, and then now it's active, right? And if we check back to our interface, it's no longer is red; it's now green. So that has been done. Next is to add the IP address, but to do so, we would need to check. First off, we need to put in the default gateway, which we can do by actually verifying what it is. So here, we do not have any default gateway set up. So we can do so by putting a default gateway that's within the IP range of the PC itself. So we can do 10.10.1. Right, now put 10.10.1 here. Then you have to repeat that for all of the other interfaces that are on a particular on each cluster. So if you're going to add the IP address, you have to make sure that you're also adding the subnet mask. It's necessary to put both clusters in the same subnet mask. So I'm going to put this one to also on 255 and this one's on 255.0, and repeat that for all of the other PCs on this cluster. Okay, I think we are so if you hover over it, you have to make sure that your default gateway is 10.10.10.1, and it's so for all of them. Excellent. The next is to make sure that your subnet mask is the same as all the rest as well. This checks. This not yet. This also checks now. This also checks. And then lastly, yeah, this checks as well. So next is to configure the next cluster and then put, we need to finish our router config. So here, we now do the IP address, IP add. They will now add the default gateway and the subnet mask, which is 10.10.10.1, then space, and you put the subnet mask 255.2555. So now we've added the IP address successfully to that interface. So what this does is we're trying to let the router know that, okay, there's this cluster on this area, and then there's this cluster on this area. These two clusters have different ranges of IP. They are both connected to different ports on the router. So communicate, this is the default gateway of this cluster, and this is the default gateway of this cluster. Because the IP addresses are in different ranges. Without this, they might not communicate. So we are done with cluster 1. Now let's get to cluster 2. So first off, we are going to assign IP addresses to each PC. And based on our lab, let me cancel this. Based on our lab, okay. The second range of IPs should be 192.168.1.3 to 192.168.4.6. Let's get into that now. 192.168.1.3. Subnet marks generated already. So as we're configuring the IP, we might as well be updating the default gateway. So we can use the same .1 for default gateway for this IP range. So the default gateway for cluster 2 would now be 192.168.1.1. So we've done for the first one, move to the second one, configure this. Or okay, next is this. This is 5 right here, 1. Okay, then the last PC here This should be the last one. PC20. Yeah, it should be 6. Yep. Default gateway, put it at 1. So we've configured each PC with the required IP addresses. So now is to configure the ports that is connected to the router. So this is gigabyte port 0.0/1. So the ports are necessary because if you do make a mistake, you'll be configuring your connection would not stand. So now we type exit to move back 1 slot. So now we've exited from configuring the gigabit interface 0/4/0/4/0. And now we want to get into configuring interface 0/4/0/4/1. And we can do so by using the same command we used for this, but 1 instead. Now we are already on that. So next we type no shutdown again to get it up and running. And then it is now up and running. So now is to configure the IP address. So just like any command line interface in almost all terminals, if you press the up key, it would list out or bring back the previous command that you've already executed on that terminal. So on this CLI is the same. So as you can see, I just navigated to the old command I executed to add the IP address. And now I just have to switch this IP address to the current one that we have. Right? 192.168. Do not forget you are putting the default gateway here. 168.1.1. So now that has been configured, we now try to communicate. Ping 192.168.1.5. Let me remember the ranges again. Yeah. As we can see, the pinging was successful. And if you notice, it sent out 4 packets, it received 3 and lost 1. So why is this? If you're going to be working on Cisco Packet Tracer, you're going to see this happen a lot, especially when you are configuring either different clusters with different IP ranges, and sometimes when you're also doing for VLANs. What this means is during the first try, it is trying to understand the network itself, trying to understand this particular address that you're sending it to. It will first of all send all of the information to its own cluster. It doesn't find that IP address, it's dropped. So now let us do this same ping command using one of the PCs from the other cluster and monitoring the activity in real time, rather in simulation mode. Let's go simulation. This is your 4, right? Then I should be able to ping .12 from here. Why is the router? Oh, okay. So, right. Just to be certain that this is part of our cluster, let me confirm this. Yeah, .5 is part of our cluster. So we can now observe this here. So we can see what's happening. Yeah, let me remove this. You see what's happening? It has, first of all, it distributes everywhere, doesn't find what it's looking for, but because of the fact that the router is configured correctly, the router would now redirect that particular PD to the right place. If, let me see our ping, select to ping it, let's see. So you can see what's happening. The router, because it has been configured, it now knows that, oh, this message is not for this cluster, it's for the other cluster, and is able to redirect it correctly. So it gives back the information informing that switch that, oh, I found this, but it's not in your cluster. This sends the information back to the PC that requested to ping outside its cluster, and it sends it back, and the router knows that, okay, we push it to the right cluster, and then this switch now knows, oh yeah, this is my address, and then it's able to distribute it where it's not, it cancels out, it gets the right information, and then it sends back the response. Yeah. So this configuration we come to the end of this particular lab, and let us see. The thing to verify that they are connected, and they are, because as we can see, the packets were all successful, apart from the first one, as I explained, which is the learning stage of the process. So most of the time, sometimes you see one, sometimes you might see two in your configuration, but you should not have less than 50% packet loss. And that should just be on the first thing. Subsequent things should be 100%. You shouldn't lose any packets. So lastly, what address type is burned in the network, in the device's network card? I think at the beginning of this lecture, we kind of spoke about that, if you remember correctly. So the address type is the what? The MAC address. I'll verify this by typing in here, capital, submit the flag. Let's see if we are on point. Okay, so yeah, we are good to go. So, do we have any questions on the okay, all right. So with this, we come to the completion of today's lecture. We've been able to go through networking fundamentals, learned about some concepts of networking itself, and then we delve into understanding network at different layers, the TCP/IP model, the OSI model, and getting like a stronger foundation in networking itself. And then we delved into packet tracer, where we've been able to establish different types of connections. First, we understood the GUI, and then we further stepped into creating simple networks, local area networks, emulating some topologies, proper topologies such as the star topology. And we now also created multiple clusters, connected them to router, and configured a successful connection between the two clusters. So we would roll up the curtains here and pick up from where we stopped in another session. Thank you all very much and have a wonderful day ahead. Over to you, Jane.
Thank you. Thank you. Okay, I guess since we have no questions, that brings us to the end of today's section. Thank you, Cedric, for the wonderful section today, and we hope to see more of you. Before we finally end, for those of you who are interested in also handling a section with us, you could reach out to us and just send an email to info@hack365global.com and you will get your response. So if you're interested, just kindly reach out to us. We're open to as many facilitators as possible. Finally, don't forget to like and share this section to whoever you know who benefits from this learning experience. And also subscribe to our channel.
Session. Very good
We have live updates.
for the culture.
That's all for today. Hope to see you next weekend. Do enjoy the rest of the weekend. Bye.